He's currently the chairman in the Mechanical Engineering Department in the University of Maryland. He has the envious achievement of being a fellow both of ASME, but also of the fellow Society, American Institute of Aeronautics and Astronautics. He has an endowed chair, and today he's going to be talking about nonlinear mechanics of drilling. I have been fortunate to work on and off on this topic for decades, and I personally am looking forward to his talk, and I'm sure that he will share my excitement about such an interesting topic. So, Bala,
thank you.
The podium is yours. Thank you.
Thank you, Paul. It's indeed an honor to be introduced by Professor Spanos for this talk. At the outset, I'd like to thank the organizers for this opportunity to be here today. So as the title reads, it's nonlinear mechanics of drilling. So my foray into this topic started almost 10 plus years ago. We had some work with the Abu Dhabi National Oil Company where they wanted us to look at drill string dynamics. So up on the top, what you see on the further right, to my right, is a schematic of a drill string, which essentially you have a hoisting system and a motor drive that turns the thing up on the top, and then you have a kilometer-long drill string that includes drill pipes, stabilizers for lateral stability, and as well as drill collars that add weight to the system, and then you have a drill bit that does the cutting action. So the question for us was to understand better the dynamics of the system. To put things in perspective, all the control is typically right at the top, right out here, and all the motion that you need to control the drill bit is out here. It's almost a kilometer away from where your control is, so it's a non-collocated control problem. And in addition, the sensing that you have is not readily available. You do have sensors at the bottom. And so this is a recording of a torsional strain provided by Schlumberger. So if you look at the strain plot, what you see in this plot out here, this time history is typically what you would see for nominal torsional motions when everything is regular. It's at 50 RPM. But when you have stick slip, you see phases where the speed goes to 0, and then it winds up to speeds which are 2 to 3 times your actual rotational speed. Now, so this is one aspect of the dynamics. So in terms of So in terms of the dynamics, so what you see out here, this is one aspect. You also have the different other modes. The axial motions, as the drill bit bounces off the surface, it's called a bit bounce. And you have bending motions, which Professor Spanos spent a considerable amount of time and effort in understanding lateral instabilities as well as how the bending motions affect the drill string dynamics itself. And this corresponds to torsional vibrations that I talked about. And this, if you have any eccentricity in the drill string, given its length, it's quite possible that could induce some dynamics as well. So in terms of things to note, so we do have delay effects since you have a cutting action, and also the drill string motion is nonlinear in character because you have contacts and impacts with the borehole, its outer shell, as well as the bottom. Nonlinear friction forces, you could have coupling between the different vibration modes depending on the frequencies that they have and the nonlinearities in the system. And of course, in this case, given the length of the system, you do have large deformations as well. So in terms of comparisons, given the length of the drill string, it's about 1 kilometer long, and the diameter, which is about a few centimeters, so the aspect ratio is over human hair in terms of comparisons. So in this system, So one of the starting points when we were talking to the Abu Dhabi National Oil Company is they took us to the National Drilling Company in Abu Dhabi to show us these 2 failures. So this one out here is what is called a washout failure, where purely due to bending motions you develop cracks in your drill pipes, and that leads to failure of the drill string. In the second case, this is a torsional failure when you have the two drill pipes meeting at one location. In between you could have torsional strains that kind of overwhelm the system, and things could come apart as well. So this is much more dangerous than this one out here. But nevertheless, if any of these failures happen, each time that happens in the system, you got to take the whole thing out and replace the whole drill string. It could cost you several $1 million. And it also cuts down the time that you have for producing oil or gas that you're after. Okay, so in terms of where we are with this, so this in a snapshot covers roughly more or less where we have been in this area in terms of different models that we use. So on the far left, what you see is an actual illustration of the whole system itself with the crown block, the traveling block, which you use to provide the hoist load, along with the drill collar weight that provides you weight on bit, or the drill bit, and then you have the rotor out here, and the whole string arrangement. The drill collars, the drill bit is what is typically referred to as the bottom hole assembly. So to study the dynamics of the system, this is, of course, if you were to write the partial differential equations out, that include the time delays and everything, so it's an infinite dimensional system. So one reduction that one could do, this is the spatial dynamics. You could discretize the system, and then you could end up with a finite element model, which is orders of degrees of freedom could be 100 to 1,000 if you wish. And then if you want to isolate the physics, for instance, if you'd just like to understand what happens between the stabilizers and the bottom hole assembly, you could come down and have a model which is of 10 degrees of freedom. And if you're constructing a setup in the lab, this is an illustration of what we have in our lab. This is a section between two stabilizers. The frequencies in this case are about less than a hertz in the first torsional first axial modes, and they both are about the same thing as what you would see in a field. In a field experiment, the torsional mode would have frequency about 0.5 hertz, and the first axial would be about 0.7 hertz. So that ratio is preserved in the experiments as well. So here we have a rotor-stator arrangement to mimic what you see out here in the essentially a bore well, essentially with a thing that rotates to the bottom, and then we have a slip ring for strain gauges instrumented on the string, and then you have a servo motor through which we provide the rotational inputs to the system, and a camera to pick up the motions of the disc itself, which one could use to look at eccentricity as well as contact and no loss of contact type of motions. Okay, so in terms of the model that we have, which we worked with, this is an illustration of what is in the model. So at the very end of the drill bit, so you have the drill bit, which is in this case has 4 blades, 2 of them as illustrated out here, and essentially when we cut a piece of rock, typically the cutting depth is typically about 0.1 millimeters. And so whereas the displacements could be much higher than that. So if your displacements are much higher, then you could lose contact itself. So that instantaneous depth of cut is defined by where you were previously, z of t minus tau, the vertical distance, and z of t, the current state. The difference between them is the actual instantaneous depth of cut. So that that's very similar if you do manufacturing with materials. It's very similar definitions that one would use for milling processes. So in this study, we went through and got the dynamics of the system played out. And what you see in this rendition out here, with the angular speed, which drops to 0 at certain locations. In certain places, as you saw in the field data, you see a speed up in the RPM itself. And likewise, if you look at the axial speed, you look at places where the speed goes to 0, there's sticking between the rock and the drill bit, and places where the speed becomes negative, that indicates the drill bit is not in contact with the rock. So you have bit bounce in the system. So both of those were captured in the system, the model which I'll describe in a bit. But for this case, where essentially the drill string that you have is several kilometers long, the drill collar, which is a heavier section, in this case is about 100 to 200 meters long, and the drive torque, the 2 control inputs for us in this case, for bifurcation purposes, are the RPM that you put on the system up on the top, and the penetration speed V naught. So these are the two control parameters that you'll see me referring to as we go forward in terms of how does that affect the stability of the system. All right, so more in terms of modeling. So we took the, if you were to focus at the bottom, the drill bit itself, we could define the weight on the bit and the torque on the bit in terms of two components, one being due to the cutting action, the WBC part of it, and the WBF is a friction part, likewise with the torque as well acting on the bit, and both of them you find they're highly nonlinear. You have the ramp function basically which tells you that it increases with the depth of cut, and you also have a heaviside function basically when you have loss of contact, those things vanish. And so here I've illustrated two, basically essentially dry friction, loss of contact, and how they play a role. Apart from that, another aspect to consider is what I had mentioned before, the depth of cut and how the time delay enters the picture. So essentially the time delay in this case is a state-dependent delay. So what does that mean? So if I were to start at one location, and if I were to come back to the same location nominally, if I didn't have any dynamics, it would purely be based on rotation speed. Now in this case, theta is an angular state whose dynamics also affects how long it takes for me to come back to that position. So the tau in this case is no longer just 2 pi over your rotation speed, but rather something that you need to find through this relationship out here. So the tau is an implicit function of the angular states Vn, Tn, T minus tau, and T itself. So you have to find it numerically in this case. So that's what makes this problem a little complicated. So state-dependent delays are not unique to drilling processes. You could also have milling in which these things occur. They also occur in additive manufacturing, where they occur in other places as well. But with the state-dependent delay, in terms of stability analysis, it does get difficult because a true linearization does not exist. So one has to come up with approximations to provide you the local properties as you would with that particular delay itself. Now, throughout the talk, one of the cutters that we use is this PDC bit that you see up here, which there's certain parameters specific to the system, like the radius of the drill bit, the wavelength of the flats out here, depending on the rock that you cut, the specific energy, the geometry around the drill bit, the parameters of cutter force inclination, those angles out, the friction coefficient. And of course, these models are not new in this work. They've been used for more than 20 years. Emmanuel at the University of Minnesota has been working on this topic for quite a number of years in terms of these models. So those are the same models that we use out here. What is new in this work is how we model the dynamics and the bit-rock interactions. Okay, so in terms of the model that we develop, we basically focus on axial torsional dynamics. So basically what that means, up and down motions of the drill string and the twisting motions of the drill string. So at each state you have a vertical displacement, that's the rotation, then we have elastic interconnects in between, and through that you can come up with a reduced sort of model in which all the delays are captured on the right hand side where the weight on the bit and the cutting torque up here. And tau again is a state dependent delay, and so if I pick NC is the number of elements that we pick in the drill collar, and NSP is the number of elements we pick for the drill string itself. So in this case, typically you'll see that I pick about, the total number of segments I have is about 32. That would mean about 64 states, and then 64 as Z and phi, and then in terms of the state space, we 128 states in the system. Now, if I were to take that system and look at how the system behaves, this is a rendition of the time histories with the axial motions and the torsional motions. And again, what you see before in the plots, that you see a negative velocity, a negative speed indicating a bit bounce. That's the drill bit is bouncing off the rock. And you also see places where there's sticking motion. So essentially the bit is in contact with the rock and it doesn't turn. And it slips where the speeds of rotation are much higher than your imposed speeds itself. Now the question then is, okay, with this, how does the wave behavior occur? How does the wave dynamics look like?
You could just, I think this one you can just click here, I think. Yeah.
So what you'll see in the illustration is if I were to go through actual drilling operation, based on the system that you see the waves traveling up the drill string. This is basically the distribution of the von Mises stress as the wave runs up from the bottom where the cutting action takes place to all the way up in the top. So if I return back to the slides, what you'll see is that the shear strain is dominant in this case compared to the normal strain or the axial strain. And that's what you see in these plots out here. The shear strain is 1 order of magnitude than the normal strain. And you could also pick up some features like there's a node around location number 26 in this plot, and a 9-tie node somewhere around 15 in the shear strain plot. So essentially, this model that we have allows you to look at the wave propagation through the drill string. As you initiate the axe right at the bottom, how do those waves travel up? And what we see, at least for this particular choice of parameters, the shear waves dominate compared to the axial waves in the system. And this probably also explains why the torsional failures are much more possible in these cases in the system than the one due to axial strains. The torsional failures and the bending failures, which you, of course, didn't account for in this particular model. So now, if I move forward, the question now is the stability of the system. How can I come up with stability plots where basically if I know I have a certain cutting speed, cutting rotation speed, and a certain cutting depth, or a certain cutting specific energy, there are parameter regions where I will have a stable dynamics. So to do that, in this case, as a first approximation, we're going to assume the state-dependent delay as a constant delay. The next few slides I'll come back to state-dependent delay, just to get a sense of the dynamics. We approximate the state-dependent delay to be a constant delay. Once we do that, then we can use the semi-discretization method that Innsberg and Stefan have worked with. So before we get there, if I take the nonlinear system, linearize the system around a certain operational range, and then I take my delay, in this case I divide it up into 40 segments, and then that shear M in this case stands for the number of segments I have for the time period due to delay, and it's a number of states, so just 32 out here. Then I can go from a linearized system to a high dimensional map, and then I can look at fixed points of this map and eigenvalues of this map to see if the corresponding motions are stable or unstable. So if we go through that and take note of that, recall that if I had a multiplier that's outside the unit circle, then system is unstable. If everything is inside, then it's stable. So if I take it to a degenerate case where I just have one segment representing the whole system, the region inside is stable region out here. So if I would initiate motions inside that region, things die away. Whereas if I hit any of these boundaries, which are loci of Hopf bifurcation points, I end up with a limit cycle motion. So this basically, in those cases, you end up with whirl dynamics or stick slip dynamics, in this case, in the system. So however, interesting to note is if I increase the number of segments, the stable region that I have available for me keeps shrinking in size. So in these systems, it's very likely that stick slip will happen if you take a truly distributed parameter system. So in our model, we don't have a distributed parameter system, but we're very close. We get close to it as we increase the number of segments in the system itself. But however, so this again, if I were to design the system or operations of the system, this is a region which I would like to stay within. For example, if I take the total of 4 segments, the purple region is my stable region. If I go anywhere outside the red lines, I would become unstable. So again, so this indicates that in these systems, when you model these, the level of spatial discretization that one uses to infer about stability is very important. I think if it's a lower order system, it's quite possible that for certain parameter ranges, the results that you get will not be accurate. Okay, so to take a closer look at the state-dependent delay, so we're going to come back to a reduced order model. So this model essentially includes this whole drill string system. It's a 2-degree of freedom system with a boundary condition through which you get the penetration speed and the rotation speed. And again, I have the delay terms captured in these 2 terms out here. The system has an equilibrium solution in this fashion. So all that means is and the system is in equilibrium, the drill bit is basically moving at this penetration speed that you impose on the system, and it's spinning at the speed at which you impose up on the top. So that is my baseline case. If everything is stable, that's what it should be doing. So to get the stability of the system, so again, let me just recall some parameters for later reference. N is the number of blades, psi is a cutting coefficient, V naught is a measure of your penetration rate, and omega naught is a measure of your spin rate. And again, your state-dependent delay appears in this equation out here. It's an implicit delay. We do some non-dimensionalization in the system and go through and put it in this form. Essentially, what I have is a usual state space form with the delay term and its implicit delay that's a function of the states. So once you have the system, you could do a linearization. So this linearization is what I mentioned before. When you have a state-dependent delay, this linearization is what they call quasi linearization, because it captures the local dynamics of the system state-dependent delay when we make this approximation. So in this case, you capture the delay to get you get your Jacobian matrices for the different derivatives, and this is the additional term that we get because of state-dependent delay, all of which is constructible in this case. And then if you go further, the key point is if had I not taken the state-dependent delay into account, I would not pick up these terms highlighted in blue. So essentially, the penetration speed effect, which is capital V naught, is something that would not appear in the system stability analysis had I not taken the state-dependent delay into account. That's a major change between a constant delay case and the state-dependent delay case. And then one could go through and do the usual stability analysis. You get the characteristic equation. This is several pages of algebra, but pretty straightforward to do. You could end up with this polynomial, which you can study for the stability properties of the characteristic equation. And then essentially the stability criteria is the same as what you saw before. If I have my eigenvalues, in this case I have a negative real part, I have a stable system. And then when the tau delay is 0, you can compute your case and then find out the eigenvalues all have real parts less than 0. System is stable. If I go to the case of state-dependent delay, then here's the D Subdivision Method. Essentially what that is we start out with a case with the delay is 0, find out all the characteristic multipliers, and then follow the ones which are on the imaginary axis and see how they've changed as you change one of the parameters, like in this case, the spin rate of the system. So once you do that, you could get your the cutting depth, the penetration rate, as well as the RPM, and the phase relationships are useful in this case to pick up your omegas, and through that, these values out here. So once you have all of those plots, all of those computed, you can construct a graph like this. In this graph, what you see on the x-axis is your spin rate, and what you see on the y-axis is your penetration speed. And basically, if I pick this value of damping, essentially, if I'm outside, this is unstable. If I'm within this region, it's stable, just similar to what you saw in the numerical studies. Now, of course, if you decrease the value of damping, the region of stability decreases, so that's what you see out here. The state-dependent delay affects this particular top branch of it, and the constant delay affects this portion of your system. So again, in this case, the point being that with the consideration of state-dependent delay, you pick up the effects of the penetration speed on the stability of the system. Had I just did a constant delay model, I would have missed picking up that effect. Okay, so you could also do other plots into other parameters. In this case, I have the RPM again, and the cutting coefficient out here, depending on the rocks that you cut. And these are typically in the range of 30 megapascals to 60 megapascals. This is non-dimensionalized in this case. And again, you can see how these boundaries change as we change in terms of the penetration rates in the system. So this is a lower penetration rate, and this is a higher penetration rate, and this is even a further one. You can see how the stability boundaries are changed. This allows you to calibrate on how fast could you penetrate the rocks that you have in the system. All right, so the question then is, if I have a half bifurcation of the system, is that supercritical or subcritical? So why would we care about it? Well, if it's subcritical, there could be large transition for after your instability, that you basically have a jump from a steady state to a large amplitude motion. Like in this case, if I'm out here, as you change the parameter after you cross the bifurcation point, you'll have a large amplitude solution. But if it's a supercritical, when I transition from an equilibrium state to a world state or stick slip state, the transition is much more smoother. Okay? So now the question is, how do you do that in this case? So all the nonlinear terms are on the right-hand side. Those are all because of state-dependent delay in this case, because of approximations that we made in this model. So what we do is we take that state-dependent delay and make it explicit by expanding in that particular form that you see out there. And so essentially it's of the first two orders that you expanded these terms out to, with this three-level nested construction. So once you do that, you can go through and construct your bifurcation diagrams, and you find that for certain cases you do have a subcritical bifurcation. In certain cases, depending on the damping level, you end up with supercritical bifurcations. So your damping, again, is a critical parameter. Below certain damping thresholds, you do end up with supercritical. So in this case, if you wonder as to where the damping comes from, the damping comes from the drill fluid that you have, or the drill mud that you have between the drill pipe and the outer shell. And of course, if you had a controller that you could use along with the dry up in the top, that's another way to impose damping as well, which I'm told is fairly hard to do in practice. So most of the damping comes from the drill mud in this case. So these things were done using these constructions was done using BIFPAC. I think there's a delay differential equation software that was used to construct these plots out here. So that concludes one part of the talk, in which the whole goal was to look at stick-slip dynamics and how do you predict those, and what type of features does one need to take into account to capture those. So instead of isolating the physics, the next part I'll segue into is world dynamics. So whirling motions are another instability that happen in these strings. So here I'm isolating the system and looking at a case where there's no cutting action. I'm purely looking at whirl dynamics. So I use an extended Jeffcott rotor model where the whole system is collapsed in the plane to this rotor. The bore wall is this outer shell. And essentially these elastic elements that you see here are for illustrating the contact interactions that we have. If I were to collapse the system all the way down to just the torsional oscillation equation, what you'll find is that without any contact, the frequency response curve will follow this particular graph. With contact, you'd have branches of backward whirling, forward whirling. And so when you have backward whirling, you rotate in the opposite direction of the imposed rotation. Like in this case, that's a rotation in which the string would be rotating. That would be a drive direction up on the top. But the forward whirling with contact is when the rotor is actually making contact with the outer shell, and this one is a case without contact. So then ideal case would be, if you're drilling, you'd like to keep the drill bit at the center of the bore hole, and the forward whirling without contact would be the ideal situation. But you typically end up with one of these situations depending upon the drill mud pressure, as well as the friction that you have, as well as other interactions. So this is the experimental setup that we have in our lab, that we construct so that the string properties are more or less the same in terms of frequencies that you will see in the field. The damping ratios are very, very light. Again, in this rendition, what you see is the rotor and the stator, and we have strain gauges that we use. And this is a slip ring. So if I, thank you. So if I were to look at these videos, so what you see on the left side the other one. Yeah. So forward whirling, so in this case, the rotation speed is small, and it's about the same as what you would say, what you put on the top. So if you go to the next one. Okay. Yeah, so in this case, it's a dangerous state, so you could see that you have a low frequency input, but the response has a high frequency. So this is an example where you have a low frequency energy input into the system being converted into high frequency doing backward whirling. Okay. Obviously this is a state you'd like to avoid because it could lead to breakage of the drill string itself due to torsional failure. Okay. So the question then is how does one control these states? Is it possible to move away from the states? So the backward whirling frequency, as you can see, is the radius of the rotor divided by the clearance. So this ratio is large. That's why it's much higher than your drive input. So if you go next slide.
Next slide.
Yeah.
Video.
Yeah. No. Okay. I got it. Okay. So what we did in this case, we tried to use noise to see if we could move from one response branch to another response branch. So these are experimental results. So the experiments pretty much are aimed at seeing if I could move from this branch of forward whirling without contact to the backward whirling branch. And so we start at the drill speed and then we impose noise in the system, the servo motor, and cut it off. And what you see, I'm moving from a forward whirling state to a backward whirling state. So essentially the noise allows me to move from one branch of solution to another branch of solutions. Okay, so this is noise assisted steering. So this is something can be done. I think most drill string operations these days have a secondary motor which is not on the top but somewhere down, further down the drill string itself, which could be used to facilitate secondary frequency inputs into the system itself. Although this is not something you like to do in practice. You're basically going from a state where the amplitude is low to a case where the whirling mode is fairly large. Right? And then we did a model for the system. Essentially, this is a projection on three directions. One is the two transverse displacements, and the size your torsional state, and the theta is up in the top, the torsional state up in the top. And then the feedback control with noise is captured out here, and the delay is also captured in this case. So essentially, integrating the system is a little tricky. So because you have noise, so when noise is present, you use an Euler-Maruyama scheme. When noise is absent, you use a Runge-Kutta scheme, and you switch between the two to capture the true dynamics of the system. So if you do that, you pretty much capture what you see in the experiments. You have the motor outputs. Of course, the numerical results are a lot cleaner. You go from a forward whirling state to a backward whirling state like you saw in the experiments. So essentially, noise could be a good catalyst for you to move from one branch of solution to another branch of solutions. In other experiments in the lab, we've also tried secondary frequency additions, which again helps us to do response steering. And this is another example where if you've gone from forward whirling without contact to backward whirling without contact. So the ideal case for us would be to move from backward whirling without contact to forward whirling without contact. So that we have recently been able to show that's possible in simulations, but the path is pretty complicated. So that's something we plan to study in the future with the experimental setup that we have in our lab. So in terms of what I showed you today, what I discussed with you today, what you see up at the top, the reducer model is very useful to understand state-dependent delay effects and how does it affect your stability regions. Of course, if you didn't take the state-dependent delay, you miss a penetration speed. The bifurcation analysis shows important damping parameters and controlling nature of the bifurcation, that is from subcritical to supercritical. Of course, in all of this, in the reducer model, the mechanics is the key. As you saw, how we model the bit rock interactions is very important, and that the friction that you capture there, the loss of contact, all of those are key aspects. The experiments are useful to understand world dynamics. We also done other experiments in other lab with cutting, where we see similar type of studies. The high dimensional models are quite critical to understand the complex dynamics of the system. Of course, noise as well as other secondary frequency inputs could be useful. I think in the field experiments, they're already, I think at Halliburton, they're already trying secondary frequency inputs to control dynamics. So those could all be in line with what you saw out here. So in terms of future work, this is a study that we've been doing with Qatar University, where essentially we have a similar setup at Qatar, and what you saw before was without the drill mud, and with the drill mud you see a stabilizing effect as well, and the backward whirling can be quite dangerous. In this case, it was so severe that the whole drill string setup came out of your borehole itself. So again, this is ongoing work with the drill mud. Again, has a big influence on the dynamics. Of course, the damping, as I mentioned before, that will be useful to reconcile with as well. So in ongoing studies, axial torsional dynamics is something that we're revisiting. I think the reason being, I think in all the prior studies, buoyancy has not received much attention. Oops. So buoyancy is something that we're capturing in this case, and also the top drive is getting a lot of attention these days as you drill things deeper and deeper. You like to make the top drive very stiff, and in some cases what that means is like a fixed boundary condition up at the top. In other cases, depending on the depth, what you like to do is you like to have a combination of stiffness dampers and inertia to capture the top drive itself, and this model will allow you to go in that particular direction. And another aspect which is important to reconcile with is the bit-rock interactions. So in all the cases which people have looked at so far, people have not captured the multiple regenerative effect. So essentially that's similar to what you see in manufacturing. If you're cutting something, you may not be cutting for at least a couple of passes before you cut again in your third pass. So that time interval that you miss, so twice your rotation speed or the delay that you get, is what is called the multiple regenerative effect. So when you have a multiple regenerative effect, what that means is your drill bit is not in contact with your rock for some time. So in this illustration that you see, the solid lines are when it's in contact, and the broken lines when you lose contact. So when you lose contact, the state-dependent delay along with the multiple regenerative effect, when there's no contact, the delay effect itself has a different picture. So essentially you have a piecewise system over different regions whenever you lose contact with the system itself. So this makes it more complicated, but it takes it closer to reality. So if you do that, the picture that you end up is quite complex. So essentially, when you have stable drilling, you could capture basically a steady state solution, and you would see the different passes follow along this one. So essentially what I've shown is 4 blades. So expanded out the angle for one of the blades, so it's 90 degrees. And as you go further out with stick slip in the system, you have periodic oscillations. This is what happens drilling with stick slip. When you have drilling with loss of contacts, bit bounce, you end up with a quasi-periodic solution. And you have a combination of both, you end up with a chaotic solution. So this is still a topic for ongoing study for us, but this is pretty much where we are today. Thanks for your attention. I'm open to any questions or comments that you have. Thank you.
Are there any questions?
Well done.
Okay, so this was a very comprehensive overview of a real problem, right?
Yeah.
So there are so many questions, but I'll focus on one. When you have the noise, which I don't know yet if anyone in the world incorporates as a controller, but when you have the noise and you see this jump for without the noise and then the jump transition, during the non-stationary response with the noise, are there any topological distinct outcomes? It would be great to have a fractal measure to see if there's an attractor in there, but can you do any type of analysis and pick up what frequencies are more important than others during this?
Yeah. Well, I think I don't have a straightforward answer, but one thing that we're looking at is what path should the trajectory take? How do I steer the system along a certain path? So for that, I would need to know the solution structure, like you're talking about. So which solutions exist where? So based on that, so I could go from backward whirling, for example, if those are periodic solutions in one region, I would like to go from that domain to another domain, to a region where forward whirling with contact happens, and then from there I can move to forward whirling without contact. So there's a path that I can develop based on the regions in which these different motions exist. Now, I think using noise to control your dynamics is a broader topic. So if you have to move from a chaotic state to a periodic state, you could essentially, take a saddle point. If you can take the stable manifold of the saddle point to move it away from the chaotic attractor, and then take the unstable manifold to move you to a periodic orbit. So that's possible. That's one path that one could take. So if you talk to people in physics, they do talk about probabilities of which path one should follow, and which path has least likelihood of happening. And so there's a little bit of work in that space, but we have not connected that to this particular one. The closest we have come to is planning your trajectory with noise to see which direction it should take.
Thank you.
Any other question? Yes, sir.
I was wondering, in your opinion, because you guys work in this area for this long, what are the future directions of research in free string dynamics, like the major directions that you can see in the future?
I think he has done an excellent job of talking about it. One of the things that I want, first of all, I would like to compliment you on a wonderful talk for a very for a very complicated problem. But the question that I have, have you considered the option of modeling the interaction of the drill string with the wall? Because some of the work that we have done is that you use like Hertz's law for the nonlinearity that you are going to have when the drill string hits the wall. I am not sure that I show in the analysis.
So I think we didn't take lateral dynamics into account in this study. We focused on axial and torsion dynamics. As Paul mentioned, if you start taking lateral dynamics, which becomes very important when you do directional drilling, where the drill string is not straight anymore, but rather curved at a certain angle. So lateral dynamics does become important. And the frictional contact models that you use become very critical. So in terms of going back to your question, at least there are two directions one could think about. One is deep drilling. So deep drilling would basically mean if you're drilling in the ocean, how deep could you go to hit the oil beds way below? So that's one area where the buoyancy effects become very important. The second is when you're drilling for oil, a certain reserve may run out of oil, so you may have to go a little bit at an angle.
Horizontal drilling.
Horizontal drilling. So for that, the drill string will be curved, will be curved. So in that case, actually having whirling motions could be helpful for you, because you could take advantage of that to make your borehole itself bigger as you go through. And so those are two ready directions. But you could use the reduced order models as a good toy problem to look at state-dependent delays. Like I said, additive manufacturing is a case where you see inkjet printing. It happens there in that case as well. So you could use that as a platform to study those things too.
If I may, there's another thing for which the companies are very protective of data is that if you want to do decouple analysis and you deal with the forces on the drill bit as imposed kinematics, then it would be very nice to have information about the spectrum of the moment and the forces which are applied there. And clearly you have two drill bits. One is a polycrystalline, the other is the tricon, where the spectra of the forces at the moment are different. It would be very nice if everybody was doing it.
I think Professor Spanos makes a very good point. I think the whole study that I had here was for a polycrystalline diamond bit. The tricon bit has a different dynamics by itself, so the friction and everything there makes it. So people are looking at spacing of the pitch blades. they're looking at how to make it different. So the drill bit is another area where people are spending a lot of time and effort these days as well, because those are pretty expensive.
Alejandro.
So in other contexts, in slip oscillations, often this can give us in terms of the friction, the drive friction decreasing in some part, some region of velocity. Is this qualitatively different, or according to you?
So I think in this model, if we went through details, you'll see we use a velocity weakening model in this case as well. So that's similar to what you would probably see if you put something on a belt. So it's very similar. So the only thing which out here is, depending on how you carry out the expansions, you could add additional terms to it. But qualitatively is very similar in terms of the modeling.
There was one other question. Okay, go ahead.
So, you have been speaking about various types of bifurcation points. Finally, the last picture is typical, showing that there should be a lot of them. Nevertheless, in the very beginning, I noticed that you have mentioned also the global Hopf bifurcation, which is rather of Andronov width type, which leads to complete change of the shape of solution. What's the interpretation here? It's not very often to see this type of bifurcation.
I mean, I didn't mention global half. What I mentioned was could have a codimension 2 point where the two branches meet up on the top. That's a degenerate point. So in those cases, I think the model that we have cannot really tell us what's going to happen beyond that. Right? So, but if you build into the numerical work, you could potentially see what the post-bifurcation state would be. That you can do for if you get an unstable region, as you traverse through it, you can develop a series of bifurcations, like in this case, where you go from a fixed point to limit cycle.
Yes, but nevertheless, I was interested only in what it means here, the global bifurcation of Hopf type.
Maybe I think we can continue the conversation a little bit later, so maybe somebody else can pose a question or can give the speaker a break. Any other question?